This video will cover the subset sum dynamic programming problem. The playlist has a couple of videos on dynamic programming to watch before this one, but those are really the only prerequisites. This will be part of my You're Not a Freaking Moron series. In developing the algorithm, we'll wander through a couple of different possibilities. If you haven't seen a problem before, there's no reason to think that you would just jump to a polished, working solution first. That makes this video long because making and fixing mistakes takes time. If you just want a more polished version, the video description has an indexed table of contents. You can just skip ahead to the third attempt once you know the problem definition. Subset sum is a very well-known problem. We'll look at one of the simplest versions here, which can be considered as a special case of the knapsack problem. Given a set of positive integers and an integer k, is there some subset of the integers which sum to k? The set is allowed to have repeated values. If you want to have two different 4 values, just include two 4s in the input. I will index from 1 instead of 0. It makes the notation a little cleaner, but nothing changes conceptually. Going to our dynamic programming template, the first goal is to come up with a recursive solution to the problem. What does a solution mean here? We're looking for a yes-no answer. But if the answer is yes, you might also want to know what subset is used. If the answer is no, there isn't much more to know about it, unless you want to know something close like the largest subset sum no bigger than k. Let's assume for a minute that the answer is yes. Recursively, we might think, if we knew one integer that went into the sum, we could then recursively figure out how to build an answer with the remaining items to make whatever's left over from the target sum. If we want to think of it in terms of our flaky friend from the previous video, if that friend whispers, "Use the 4th," you could do that. And then you'd need to reconstruct the remainder of k with the remainder of the integers after the 4th is taken out, or the 7th, or whatever Obi-Wan tells you. More generally, if you want to include the ith integer, the recursive question becomes, using the set of integers minus the ith integer, can we find a subset that equals our sum minus the size of the ith integer? We can write a recursive program to answer the question that way, trying all possible values of I. If no value will do, then it isn't possible. I won't animate that here because even though it's easy enough to show different target sizes, it isn't so easy to show the different sets of items I can choose from. Looking at our dynamic programming template, that's going to come up in our very next step. If I take an arbitrary item out of the set, creating a new set for my recursive call, there are a lot of possibilities for that remaining set. Starting with the original set, I try to take each item out individually. From each of those sets, I try to take each remaining item out individually. And from each of those sets, I try to take each remaining item out individually. Right away, we see that we're going to have a lot of recursive calls and a lot of repeat calls among them. If I take 2 items out of the set in either order, both of those would give me the same recursive call. If I try putting half of the items into the subset, there are n over 2 factorial ways I can do that with the same n over 2 items. That's a lot of times to repeat one recursive call. That repeated work is a hallmark of dynamic programming and leads to the next important question. How many different, distinct ways do you call the problem? Even if you exclude repeat calls, it seems like you can get lots of distinct subsets of your original set. In the worst case, maybe you end up considering almost every possible subset of that set, and there are 2 to the n of them. That's bad. For decent-sized n, we don't have 2 to the n time, or even worse, space, to store all of the problems we want to look at. For dynamic programming, you need to have a reasonably small number of distinct calls, but we can't guarantee that here. We're probably hosed once we try to allocate a table to hold our solutions. So what do? No, that's not right. No, we go back to our recursive solution. Is there a way that we can recursively solve the problem with fewer distinct subproblems? We've seen a hint. A lot of our repeat sets came from using the same possible sets of integers that we got to by considering integers in different orders. You can impose your own order to remove things. You don't need dynamic programming to avoid those repeats. It's kind of a waste. Instead of guessing an index to use, we can guess the lowest or highest index to use. That will lower the number of repeated problems tremendously, so we should see what it does to the number of distinct problems too. Should we use the lowest or the highest index? They're conceptually the same and both work fine, but I prefer the highest index. If you want to talk about being left with a set of X items and you remove high indices first, you'll be left with indices 1 to X. That's a lot cleaner than indices n minus x plus 1 to n. So let's assume that we know the highest indexed integer to use. If that index is 33, we're left using integers with indices 1 to 32 from the set to build the target sum after you subtract the 33rd integer. Or, for the ith integer, it leaves you with indices 1 to I minus 1 in your set to build the remaining target. Try all possible I. How much better is this than our first try? If we always just remove integers from the high indices of the array, and we start with n items in the set, this approach has only n plus 1 possible different sets it will ever be called on. That's much better than the 2 to the n possible sets we had before. That lets me write this recursive version more cleanly. I don't actually have to change the set like before. I just add an integer parameter telling me how much of the array that I can use. That looks much better than our first attempt. The parameters are clean enough now that we can animate the recursive calls. For this small set, let's start with an example where there's no solution, sum 46. For that top numbered node, the 6 means that you can use any of the first 6 integers from our set, and 46 is the target sum. Even with this small set, we can see that the tree already starts to look a bit big. On the other hand, the code is written so that once you see the answer is true, it shortcuts back to the root. So for the true instance with target sum 45, the tree is much smaller. So now, when we do our parameter analysis for the Memoized version, it's much better than before. We have a target sum parameter that can go up to k. S tells us all the integers we can use to start the problem, and the other parameter specifies how much of that set we can use for this problem, where we use the head of the set. It can go up to the length of the array. Now that our parameters are more under control, we can memoize that recursive program. The only changes are in red. You allocated a table for answers, and before making any recursive calls, you check the table to see if you already have an answer. If you compute an answer, store it before returning it. We can also put most of the base cases right into the table itself by making its indices start at 0. Those changes are in red and will eventually help to make our iterative code look cleaner. Now if we run this code on that false instance, we can see some parts of the tree getting pruned off. Do you see that 236 node near the center of the tree? Later on, the program gets called again with those same parameters, so that second call won't make any recursive calls or have any children in the tree. In this example, the number of items is really small. There'd be a lot more drastic pruning if the set were large with multiple subsets that had equal sums. Moving to our next step. If we want to go iterative, we analyze the table. To fill an arbitrary box in the table, like 540, it can make one recursive call to check a value on each of the rows above it, where the column will be something to the left of the current column, depending on the size of the integer that you're trying to put into the summation. Those are the spaces checked by direct recursive calls, no indirect ones. As long as you fill the table using an order that fills everything above and to the left of a square before you get to it, you'll be fine. The easiest ways to do that are either column by column or row by row. And they both work, but it will be easier to see what's going on row by row. Filling in the first row, there's only one recursive call made per table location. The second row makes 2 recursive calls per location. You can already see it slowing down there. I'll fast forward rows 3 to 5, and then we see how slowly the 6th row goes. Each location might be making up to 6 recursive calls, though any box that gets a true value will stop once it finds that true recursive call. Hey, there's an optimization right there. There are a lot more true values in rows at the bottom of the table than the top of the table. If we check those rows first, when we see one of those true values, we can return true and take that shortcut more often. I'll change my code to do that and then just show what it looks like to fill that last row again. You can see it's a bit quicker. But worst case, order k n boxes still take up to n time to compute a value. So this is a worst case k n squared runtime algorithm. Going to our dynamic programming template, can we optimize this for space? To fill a box, you might have to look at one value from each row above it, so it doesn't seem like we can get rid of any of the rows. But maybe we don't need all of the columns. If you're thinking about using an integer 6, you need to check 6 columns to the left, but you wouldn't need to keep anything to the left of that for the row corresponding to integer 6. You could handle that row by row, or if your maximum integer isn't too big, you could easily use that to limit the number of columns you store for all rows. Then again, here we have a couple of pretty big items. How about any extra information we need to keep in order to reconstruct the table? Even though the table goes up to 46, we can ask questions about how to fill other possible target sums like 45. What subset summed to 45? How did that 645 slot get filled in as true? Let's highlight the table locations that slot depends on. In this case, if we check from the 5th row first, it gets its true value from the 541 location. If we had gone from row 0 first, as we did originally, it would have been set to true from the 239 location. The fact that either of those locations would do is because there's more than one way to get a subset of size 45. We can put on our blinders and figure out what extra information is needed to reconstruct the appropriate subset and finish the video in just a few more minutes. But there's a huge clue here that something should be changed. Think about what the answer at the table at location 645 means. Using some of the first 6 integers in our set, we can get a subset of 45. But even without checking all of those squares, you kind of know it has to be true if you look at the box right above it. If a subset of the first 5 integers sums to 45, of course, some subset of the first 6 integers does too. If you go down any column from the top, once it turns true, it has to stay true, because adding extra potential integers to use doesn't force you to use them. What did the 545 box depend on? All of the same boxes as 645, except not 541. It depends on almost all the same boxes. Instead of checking those 5 other locations, we could have just checked 1. And we can see how that looks logically for that location and for every location. It's really easy to miss that way of speeding up the algorithm if you happen to start down the path of our second recursive algorithm instead of what will be our third recursive algorithm. When we couldn't find a dynamic program for our first recursive approach, it forced us to change directions. We were stuck. There wasn't much choice. But here, This is much harder. The recursive program and the dynamic program worked fine, but by fully exploring the problem, there's this subtle clue towards a better algorithm. It's hard to stop something when it's working just before finishing it. In this case, we're so far into the problem, we could incorporate that observation directly into what we've done so far to get a final answer quickly, but it's worth noticing that a different recursive idea could have sent us to what will be our final answer more directly. I'll go back to the recursive design to show the development of the new approach through all of the steps. It won't take too long compared to what we've done so far, but I'm sure that some of you will skip ahead to the final iterative versions of that algorithm if you're already totally sick of me. The second algorithm was based on the question, what is the highest indexed item that you use in your solution? You tried all possible values and worked out a recursive solution to each. But our clue led us to what is a simpler question. Do you use the last integer? You have two choices. You don't use it or you do. Either way, you're left with a recursive problem with one fewer elements in your set and one of two different target summation values. That gives us a simpler recursive algorithm than before. Of course, you could make those recursive calls in either order. Now for this true instance with target sum 45, if we recursively first try throwing the last item away and creating the target subset with whatever is left, we only see a little bit of how big the tree could be. Because once any recursive call hits a true base case, the problem unwinds the recursion to return true. If you recursively first try to add the last integer to be part of the subset, it also finds an answer quickly, but it isn't the same subset because there's more than one subset with that sum. But once we go to a false instance, like 46, we can see the entire binary tree structure. Like before, the 646 label means that you have a target sum of 46 using items chosen from the first 6 in the array. There are up to 2 to the n recursive calls made because there are n levels to the tree and each one can have twice as many calls as the level above it. But like before, ignoring negative values, the target sum is 0 to k and the number of items is 0 to n for all of them. So there are order kn distinct calls. We allocate a table to hold all of those answers, and like before, we memoize our answer. I'll also move the non-negative base cases into the table. If we run this memoized version on that same false instance as before, we can see some places where our computations get pruned. For this instance, any leaf value that isn't at the same level as before is a recursive call with repeat parameters. On a bigger instance, where lots of different combinations of integers sum up to the same number, there'd be a lot more pruning. Up next is analyzing how the table gets filled in. Each table location, like 540, depends on the one directly above it and some other space to the left of that one. We can again fill column by column or row by row. Either one will work, although we can probably see what's going on better row by row. So let's switch over to that one. I also switched to check the box right above the current one first, because that check is quicker. It doesn't need an extra safety check on the index. It's clear to see why this algorithm is faster than the iterative version of algorithm 2. Here, each table location depends on only 2 others. We have kn table locations, and if you fill them in order, it takes constant time to fill each for kn time instead of kn squared. Back to our template. Can we optimize space? Each table location depends on only the row above it. If you're filling in row by row, you don't need to keep them all. You can go down to just 2 rows using one to calculate the next and going back and forth between the 2. Here, row by row actually works better than column by column. It isn't just an easier animation to understand. Can we go down to 1 row? Well, if I just overwrite the same row, I run into a problem. For integer 17, when location 34 looks back to space 17, that was only true because of the 17 integer I'm still actively considering. But you can fix that by going right to left each time you consider a row. If you're considering the ith integer and the jth column, columns with index less than j tell you what subset sums you can get using the first I-1 integers, while columns with index greater than j let you use the first I integers. So we only need a single row of the table instead of two. We can add a little optimization to that. Once your index becomes smaller than the current integer you're considering, you can just stop. Obviously, integer 22 won't help you fill a size 10 target because we haven't allowed any negative numbers. Last step. Do we need any more information to reconstruct the set? If we had kept the entire k by n table, we wouldn't need anything extra. That table had enough information to reconstruct answers in time linear in n, highlighted for a size 43 subset here. But with just one row, we can only give yes/no answers unless we keep extra information. Instead of true/false values, I will store an integer, the last index that was used to make the subset. -1 will represent that you cannot fill that size yet, and 0 will indicate the base case that you can fill a 0 size set with no items. So when you consider the ith integer, size j, if you can already make a subset of size j without I, it doesn't change. But if using the ith integer allows you to fill that subset size when you couldn't before, you fill in index I instead of true. Even though this is one table, it now holds integers instead of true/false values, so maybe it takes a little more space. If the number n is small enough to fit in constant space, it still takes order kn space though. One last optimization I won't add to the code. We could stop running once the last column becomes true. With this data, if the answer is true, you can reconstruct the integers to find a subset in time linear in the number of integers in that subset. If it's false, I'm just returning nil, but you could look for the largest true value, which takes worst case time linear in k, and reconstruct that set. If there are multiple subsets with the sum, this code will give you the one that minimizes the maximum index of any integer used in the subset. If you sorted the set first, it would minimize the maximum integer used. Or if you reverse sorted, it would maximize the minimum integer used. You could also modify it, store the number of items used in another array, and use that to maximize or minimize the number of items in the set you find with the target sum. We have a kn time, k-space algorithm, much better than our second algorithm. That one started with a more complex question, and by answering that harder question at each recursive request, we redid a lot of work. Is kn time good? Well, it's kind of a strange time because of what k represents. N represents the number of integers in your input, like usual, but k represents the value of one of the inputs. Suppose I give you a problem with 1,000 integers and k equals 100 million, and it takes a minute to answer. If you switch to 2,000 answers, it should take about 2 minutes because the input is twice as large. But if I keep 1,000 integers but go to k equals 1 trillion, it takes 10,000 times as long, almost a week, if you have enough memory to hold your trillion item table, which I don't. But the input size isn't really any different than it was for the smaller problem. You just changed the value of one of your inputs. To store relatively small numbers, we usually assume it takes constant space. That's called the uniform cost model. Once the numbers start getting big, it really takes order log k bits to specify the number k. That's called the logarithmic cost model. For this problem, Because our runtime is proportional to the value of k, instead of the size of k as an input, we really need that model. Kn is linear in the array length n and in the value of k, but exponential in the number of bits needed to specify k. This is known as pseudopolynomial runtime. It looks polynomial, but it isn't really, because it uses the value of an input rather than the length of an input. This problem is actually an NP-complete one. They will have their own playlist. NP-complete problems are problems where, for yes instances, there exists a proof you can hand somebody to quickly convince them that the answer is yes. Here, if there's a subset that sums to k, you can just tell the person what the subset is and they can check it for themselves. If the answer is no, you don't have to prove it. Well, this video took a lot longer than expected. I had a fresh haircut when we started, but I really want you to understand that it's normal to not always pick the best path first. It's fine. If my students came up with that earlier, slower dynamic program after only a couple of lectures on the topic, that's fantastic progress, even if there happens to be a better final algorithm out there somewhere, especially if you think about how bad their teacher is. Up next in the playlist is a dynamic programming video with a hidden dimension. Aparicium? No. Aloha Mora? Nope. Revelio? Hey, my beard's gone.